I'm Thomas from the VIAVIS Research Center, and I will tell you today about the two projects I've been working on for the last 10 years. So one of them is Pro3D, the planetary robotic 3D viewer for geological annotation of the Martian surface. And the other one is TSID, a 3D viewer for tunnel surface inspection and documentation. So interesting about these two projects is that they come from two completely different sides. Pro3D is mainly used by scientists, and they use Pro3D for making publications, for publishing geological analysis and driving the extraterrestrial exploration. And TSID is part of a commercial application which is sold as a package for tunnel monitoring campaigns. Nevertheless, these two projects have a lot in common, and I will hint a bit to you what this talk is about. Projects change over time, and some might use the word escalate, because if you work in a project for 8 to 10 years, it becomes complicated to maintain these projects over time, because constraints change, hardware changes, and requirements change, especially in research projects. So giving you a bit more context, what are these projects about? Everything started with DBIT. This is a tunnel surveying company, and they produce high-resolution laser scans attached with high-resolution images. So we have a partner, ELM Research in Graz. They have a reconstruction processing pipeline. So this data gets into the reconstruction pipeline, and they produce 3D surfaces. When you have a large tunnel like the Arlberg tunnel, which is 11 kilometers long, you are confronted with a lot of 3D data. So we wrote a visualization tool which can handle large data sets, large triangle sets basically, out of core with level of detail techniques and utilizing different caching hierarchies on a local machine. A bit later, another project came along with NASA and ESA, also in cooperation with ELM Research. So we have different acquisition platforms. In this case, they're a bit more spectacular than a laser scanner mounted on a car. We have a Martian rover, and we have satellites roaming around Mars, and they mostly take pictures. We don't have laser scanners on Mars yet. Would be very helpful, but we are restricted to images. So the processing is restricted to photogrammetric reconstruction. Nevertheless, we get out 3D surfaces, and we build a second viewer, the Pro3D viewer, which is for visualizing parts of the Martian surface. So what are the constraints of these projects? They both started out as a prototype with questions like, can we visualize this? Can we do that? And rather rapidly, the features grow, and all of a sudden, you have to build from this prototype. Also, we have short time to market. This is especially true for the commercial application, because small companies invest a rather big amount of money for them into research, and it has to pay off soon. So they put kind of a lot of pressure on you. And also with the scientific use case, funding schedules are tight, people need results, and we are building their tools, so they're waiting for our tools to evolve so they can do their own work. And in the end, budgets are quite tight, which mainly means that we are limited to very few people in the team. We have really tiny teams with one person in the project or 1.5 persons. So this is not a small team, this is really a tiny team. So I give you a bit of context here. We have the Victoria crater captured by the NASA Opportunity mission. The black and white pictures are from the satellite, and this close-up picture is Cape Desire, which was reconstructed from the rover mast cameras. So we have different levels of detail here. We have different data modalities. The same thing here is the never-ending tunnel. I'm not sure which one this is. I think it's Payen tunnel in Styria. And you can see the level of detail coloring as it continuously loads from the disk and streams the data efficiently. So we built visualization, mainly presentation prototypes, and all of a sudden we have to present more I already hinted that we have multimodal data. So in the Mars use case, in the Martian use case, there are just different data sources. They all come out in the same way. So it's not really multimodal, it's just different sources, but they are processed in the right way, but we have to combine them. For a single location on Mars, you have 8 different layers of geometry, and you have to decide which one is the best, the most recent, the highest quality layer. So in this graphic here, we see, this is from the 70s, this is the Mars Observer Laser Altimeter. So it's the only complete data set of Mars we have from an orbiter with a laser scanner. But it's very coarse resolution, so the different points measured on the surface, they are 250 meters apart, I think. So this is really coarse. You can't really do geologic analysis with that. You can't even really identify geomorphological features correctly, like smaller craters, for instance. Then we put high-res on that. That's a more actual camera. Then there have been algorithms which could improve the resolution of high-res, so that's high-res, super-res. And then we have the rover on the ground, which is really close to the surface and can produce high-resolution images and also high-resolution reconstructions. And with that, there are also improved algorithms which produce even better data. In the tunnel use case, it's a bit more multimodal. We have the triangles on here, so this is what I've shown in the video, but we also have raw point clouds because people don't really want to wait for the processing. They want to see if the data is fine before and combine it already. And they also have handheld images. So while the tunnel is carved out, while the boring machine is working, people take pictures of the tunnel face and analyze the geology of that. It's quite interesting that these both projects converge towards geologic analysis. It was not like that 3 years ago. So now we have a presentation of a lot of data, multimodal data, and now, of course, people want to do something with this data. They want to interact with it, and they want to annotate it and do their analysis. So this is a broken piece of the tunnel where some water is coming out, and we are fitting a regression plane interactively to this. Not very useful in this case, it's just for illustration that we have a 3D interaction. The same thing for the Mars viewer, for Pro3D. This is a geological outcrop on Earth of Utah. It was part of a field test. And here we have very detailed geologic analysis of different sediment layers. And also these disks, they represent the orientation of these layers. And the scientists use the orientation to reconstruct ancient river flows. This has been done on Earth a lot, and it's really interesting on Mars, and has also led to some discoveries that they actually proved that there were ancient lakes and rivers on Mars. And we can see there's a lot of dynamism going on here. We also have an interactive legend here, which changes with the boundaries. So this all has to be taken into account. So all of a sudden, we go from presentation and take a sharp right turn to interaction. And this introduces a central point through this complexity. So increasing complexity in 8 years of development reduces the productivity over time. So in the beginning, you have a really fast start, you get fast results, have nice visualizations, people could see things they've never seen before. But the progress just declines, because with every feature you put into your application, the complexity grows. And at one point, the integration overhead is so big that it takes you 2 months of integrating a feature that you have been programming for 1 week or for 2 weeks. So we were in both projects at about this point here, that we went from about 20 features in the year, in the first years, to 3 features a year. So people got a bit uneasy. The scientists were a bit disappointed, but they did not really complain. They just knew it will be complicated if they have some changes, and they rather just did not ask if we want to add something. Of course, the commercial people, they got a bit angry, because why don't we get the features we got before for our money? Why aren't we working for them? So this, of course, they're not aware of this curve, of this decline. So with this constant adding of complexity, you at some point in a long-running project, you reach the maintenance deadlock, I call it, when you don't want to touch anything anymore, because you know if I add something here or change something there, it will break something else. So in the end, yeah, you're deadlocked basically, and people get uneasy. So the main source of that is complexity, but where does complexity come from? We identified different sources. Of course, doing complex things introduces complexity, but we can't avoid that. It's research and people have their requirements, so we have to stay with that. But in terms of software engineering, interconnections between modules introduces complexity. This is known as coupling. Or the separation of 3D UI and logic is hard to achieve and even harder to maintain. That also introduces complexity. Also in a research project, it's inherent that the scope and the requirements steadily change. And also our working attitude to make it work first and optimize later often turns to optimize never. So this also is a big source of complexity. So, big question of this talk, main message is how to tame complexity. We can't remove the inherent complexity because complex things are complex, but rumor has it that functional programming might be the key to tame complexity. There's an interesting blog by Scott Vlashin, F# Fun for Profit, and he has a list of things why to use functional programming, or F# in particular. It's supposed to be concise, convenient, correct, concurrent, and we add another one, it's composable. So we suspect this to be kind of the silver bullet to this complexity problem. So, after long discussions, we decided, of course with the scientists, the commercial people didn't want that in the first place, a functional rewrite. We just take an application which has been developed for 8 years and say, okay, we rewrite it completely from scratch in F#. We move from C# OOP with a double WPF graphical user interface to an F# base and make a completely new user interface. So why do we have to rewrite that? Why can't we just port from one language to another? This is because functional programming introduces a paradigm shift. It has one central concept, which is also important to have all these advantages I've told you before. It's the concept of immutable data. So when you look at, hope you're comfortable with this C# code here. I'm not, because I'm used to F# now, but I'm sure you can read that. The main difference between mutable and immutable updates, we have here a dictionary, and we add a value with a certain key. And we see that this function here, it returns void. So it just mutates this D. So we put in an object, we add a value, and the object gets out again. We just mutated where it was in memory, and it changed its value. The immutable update with the persistent map data structure here, we put in a map, also put in a value in the key, and return a new map. So that's the whole point. We have an old map, we add something, we copy it, add something, and return a new map. So that's a fundamental difference. So is this immutable data concept feasible for a whole application? We add an object to a 3D scene, and we get a new scene. Sounds okay. If our scenes are light and there's not a lot of data introduced, but this immutable data concept is really pervasive. So if we change the camera in a 3D scene, we also get a new scene. So is this really possible to have high frequency updates with always generating everything newly? So there is a solution, supposedly. There's a programming language called ELM, and they introduced a special architecture, which I will show you briefly. So we have a model, that's our data, and we want to view this data. So by now it's still static, and we just have a view function how to represent this data. Then we introduce a user. The user interacts with the view. They click on buttons or they move the camera. So they trigger actions like change camera, for instance. And then we have update logic. So the update logic tells you, I have an old model, I get an action inside, how to compute a new model. So step right is the action, and then I compute from the old state a step right state, and then that gets viewed again, and I have completed this unidirectional cycle. So I will show you some code soon, and for that I have an example here. We have a little artwork media app here for drawing. So we're just drawing lines here. And we also can do undo and redo. So this is a very boring and simple example, especially if you expected something from Mars here. But I will show you the whole code behind this example here in these slides, and it will not be a lot. So first to introduce our model. For drawing a polygon, we need a polygon, so it consists of a list of 2D points. And this is not only our data, it's our complete application state. So we also have a cursor. That's the mouse cursor, and it's just at a certain point at some time. Then we also have messages. What can we do? We can add points to our polygon, so that's the basic concept of drawing, and we can also move the cursor. So really every user interaction is captured in a message. And then, as I told you before, an update logic takes the old model and the message, and it constructs a new model. This is F# code. It might be a bit unfamiliar. We also don't have a return type here, but F# can infer the type, and it's a model, I can assure you. So when adding a point, we get in the argument point, and we can just attach it here to this list. So these are our old points, and if there comes a new point, we just add it to the polygon. And if the cursor is moved, so when you move the mouse, all the time the move cursor action is triggered, so we construct the cursor. Actually, when I click, depends, yeah. And this is our view function. Everything you have seen is captured in this function. So I take all the points from the polygon, I take them pairwise, so 1 to 3 gets 1, 2, 2, 3, and so on. And then I make SVG lines. So we are just using HTML technology here and emit an SVG line in black. And then we also have 2 buttons, the undo redo button. So, and these 2 also trigger actions again. And this is just the window where we show our polygon. So now it gets interesting. How do we implement undo redo here? And that's really surprising, because with this immutable data concept, it's extremely easy to do undo redo. We just add it to our model and say our model has a past and a future. We create a recursive data type, so the model contains another model. And we also introduce the 2 messages, undo redo. They don't have any parameters. And when we add a point and create a new model, we just take the old model and put it into past. So we record the previous step. And when we want to undo our clicked point, we just take the actual model and exchange it with the past model. So we go 1 step back into the past. The same works for future, of course. When we undo, we take the current model and put it into future, because it will be the future of the past model. So that's a bit of a brain teaser. But actually, we just implemented undo redo in 2 lines of code, or 3 maybe. So how does this solve our complexity problem? It's not solved yet. We were talking about composability before. So this unidirectional data flow model, the ELM architecture, it's a hierarchical approach. So in the application update, you can call lower level updates. So they are just all these steps, they can be addressed hierarchically. So if we look at Pro3D, for instance, we can just take this 2D drawing, which we extended to 3D drawing, of course, and to integrate that, we just put in here the model of drawing we saw before. And for drawing, we just wrap all the drawing actions into a certain action. And we can just call the update method from the lower level app. So in that case, we actually we can approach complexity in a really concise and expressive way. So have we tamed complexity? I'm not sure if I could show you correctly that we really tamed it, but actually we did, because Pro3D and TSID are proof for that. So yes. But what about efficiency? We're here at the GPU days and talking a lot about performance. So no, we did not solve that. But what is the problem? We have a state, we have a model. We update this model, generate a new state. But that can be very expensive if you have to create new states all the time. So what you actually want to do, no, actually the state creation is not expensive, but the visualization. So if I change the camera or change a small bit in the tunnel, I would have to revisualize the whole tunnel. So that's not what I want to do. Actually, I want to only visualize the differences. I will not address this in this talk because it has been addressed at the GPU Days 2018 by my colleague Harald over there. And if you're interested in that, please look it up. The main message here is you need this diff thing. So functional programming will not be effective if you don't handle this diffing for visualization, for instance. So we revisit our 5 C's here. Is a functional program really the silver bullet? So it's concise. It's talking from my own experience here and with my team. We have less coding noise, fewer lines of code. It's easier to reason about code, so it's easier to interpret what somebody else wrote. It's very convenient with different paradigms and systems. It's also correct. We have much fewer errors. We shifted runtime errors towards compile errors, so the errors happen at the developer stage and not when the customer is using our software. So this is really one of the big bonuses. And with the immutable data concept, you also lose side effects. So this is also a big source of bugs. Concurrency, we did not really address this here in this talk, but it's easy to share immutable states because they can't change while you're using them. So the whole functional concept is it's perfect for parallelism and concurrency. And composability was really the silver bullet for basically rescuing our applications because they were close to hitting a wall. So what are the take-home messages? Don't fear the rewrite. It takes some time, but it pays off, and you can really chuck out a lot of code in F# because it's really concise. You really need a few lines of code. So it's not so bad to just, also for general development, just pick a piece of code. If it doesn't work, just throw it away and write it new because it will always be better than the previous version. Also for our team, I really realized that people were really happy to embrace a new concept, learn new things. They were really excited about doing F#, but also especially people who have been longer in the industry, used to object-oriented programming, they have a really hard time to grasp these new concepts. So shouldn't underestimate the training effort. Also, don't throw away tested static functions. If you have some functions that work, don't port them to F#. You will not get so much. You can just wrap them because many functional programming languages, and especially F#, does play well with others. That's step 5, sorry. Also, functional programming does fit high-performance applications if done right. If you can address this diffing problem, it can get efficient, and you still have all the advantages from the 5 C's. In our software, we are wrapping compute shaders with F#. We are addressing or calling high-performance C libraries. We can call any .NET libraries, so you can still use your old libraries, also your old code if you have C# code. And in the end, functional programming really was the thing for us to tame complexity. So if you want to see a live demo of Pro3D, and not only this rather boring 2D drawing thing, I can show you at our VR booth. I have a Pro3D demo running. You can also visit pro3d.space. Then here are some reading resources. You should not go over that now. That's more for the final slide upload. And we would really be excited if somebody wants to collaborate with the VRV's Research Center. We address many fields from biomedical visualization, fluid simulations, visual analytics, and geospatial visualization. That's what I'm doing, or virtual reality. And if you have a more commercial application, you can also address artworks. A recently founded startup who do cloud-based high-performance graphic solutions. Yeah. Thank you.
Okay, so any questions?
Okay, so I've seen you use pretty large data sets to visualize them and to analyze them. And may I ask you that what type of data structure and caching mechanism do you use in your code base? I mean, not in the low levels, just a high overview. Can you elaborate?
It's similar to an octree. So we get this data from your NEOM research in a hierarchical way. So you just have a pyramid of triangle layers, and they are chunked to a certain extent. In the tunnel, for instance, every 20 meters you have a new chunk, and it's just, yeah, and that's basically it. The real challenge is in asynchronous uploads to the GPU and things like that. But all this caching and this logic is not so smart, actually. It's just really fast. You don't have to think a lot about pre-caching or any scheduling logics, yeah.
Thank you.
Anyone else care to ask? Then I would have one other question.
Sure.
What are your constraints in terms of platform? You said that this is an F# application.
Yeah.
And do your end users use Windows, Linux, and what did you hook it into for doing graphics tied to F#?
Our users mainly use Windows, but our graphics backend is Vulkan or OpenGL, so that's platform independent, and there's also F# core. Pro3D and TunnelView are not yet on that level, but the whole engine is basically F# core able, so you could also deploy this to Linux or Mac. Yeah.
Okay.
And also our graphical user interface is in HTML, so that was also a factor into the decision to be cross-platform.
Okay.
Thank you.
Okay, so let's thank our speaker.
Thank you.